Yeah, it's my pleasure now to introduce our dear guest, Peter Klimek. Dear Peter, welcome and thank you for joining our Governance of Digital Practices lecture series on this first evening, as you said, Lucas. But I counted, isn't it already the fifth lockdown? Not so sure about that anymore. Maybe we can discuss this later.
Katja.
Yeah,
Maybe something
for me,
for the Q&A.
Feeling like the fifth lockdown. So,
Easily,
Peter.
yes.
Let me introduce you just a bit so that our viewers and the audience get a better understanding from where you speak today, from where you're going to introduce us to your practices. So you are an associate professor at the Medical University of Vienna and a faculty member of the Complexity Science Hub Vienna. Your background is in physics, statistics, and data science. And in your research, you aim to improve the prediction of complex socioeconomic systems. So in this ongoing pandemic, you were often seen on television and heard on radio in regard to your and your team's COVID-related research. And this research is revolving around also a set of models to forecast the COVID-19 epidemics in Austria. You are a member of the so-called Prognose Consortium, the consortium that is advising, or let's call it consulting, we'll maybe discuss this later, the Federal Ministry of Social Affairs, Health, Care and Consumer Information with regularly projections of case numbers and demands of hospital beds, for example. You're also part of the ad hoc think tank of the Oberste Sanitätsrat, which is something like a high sanitary council in the same ministry. And you have done a lot of work about human disease and healthcare systems, like how people acquire more and more chronic disorders as they age, how healthcare systems cope with changes in their workforce and more. But you have also done a lot of other things. So you have, for example, studied economic and financial systems. So I read it's all, but also new for me, very interesting. So he developed a novel statistical test to detect signs of electoral fraud. And you could mathematically prove that governments are bound to become ineffective over time. So I guess from your CV alone, I think it's pretty obvious why we are so excited to have you here with us tonight. And as the subtitle of our lecture series is The Politics of Data and Decision-Making, I can't think of anyone better suited on this first day of the whatever lockdown it is to speak with us about that. So whether or not politicians should base their decisions more on scientific advice and evidence is a question we can discuss afterwards. But in an ideal world, and in order to be better prepared for future crises, we definitely need better overview and assessment on the, for example, effectiveness of the manifold responses to the pandemic, be they pharmaceutical or non-pharmaceutical. The effectiveness of such interventions results from the interplay of many factors, like, for example, the timing of the implementation, the accompanying measures, whether or not, for example, certificates are controlled, and so on and so on. I think we will also briefly talk about this. The capacity to assess these interventions then builds on, for example, complex computational and simulation models. They can, for example, isolate the effects of individual interventions and assess their impact on infection incidence, for example. So such complex mathematical epidemiological models should play an important role indeed in guiding governmental responses during pandemic crisis, and in particular when they are used as monitoring system. And I think this is also a little bit what you are going to discuss with us today. So what's in the Q&A, so you're all invited to join us afterwards in a discussion. In this, we will discuss, for example, the current state of knowledge on assessing this effectiveness of these response measures, but also maybe their limitations. But also, I hope, the extent to which this knowledge could be and has already been incorporated into decision-making processes, and what this kind of the new demands that are put maybe also on scientists in this regard. So very happy to have you, Peter. The floor is yours.
Hello, good evening from my side. Thank you, Katja, for this more than kind invitation and for the introduction. I also first have to apologize because I just realized that this lecture is supposed to be in English, but only parts of my slides are going to be in English. But don't worry, there will be a lot of pictures in them anyhow. And yeah, I think we can fix that later on and then provide you with an English set of slides. Okay, so I'm gonna now start sharing my screen. Let's jump right into it. Okay, so basically I want to tell you how well did the measures work that we had at different phases in the pandemics and how this impacted decision making from our side. And so again, sorry for the German slides, but at the end of the day, and we are now also in this situation. So it's first day of lockdown, and everybody wants to know, will this be enough? So I like to respond to this question: enough for what? Please specify where do we want to go. But the point is, in order to answer these questions and in order to assess how well certain interventions work, so I put this here away maybe. So we have to be able to predict their impacts. So and this, as Katja said, I'm coming from natural science background, and for this I have to first yeah, want to think about. By the way, can you see my screen? So I hope now nothing of the screen is blocked. Okay, so the first question that I want to tackle is, so which kind of systems can we actually predict? Okay, so we're talking a lot about forecasting the pandemics and predicting of what will happen if we do certain interventions, but which are the systems where we actually can make good predictions? And I would say, again, coming from natural sciences, the classes of systems that we can predict is rather small. We are good at predicting very, very small systems. So we're good at predicting, so what happens if you have a spring and then you put a weight on that spring and you elongate it, and we are pretty confident in how this system will respond to a shock. We are also good, for instance, in predicting what will happen if we take two elementary particles, accelerate them to 99% light speed and smash them against each other and then measure what comes out of this. We are also good at predicting certain behavioral rules in sociology. So for instance, like triadic closure, social balancing, and similar similar laws. Why? If the system is small, if it contains only a few number of components, then we have a good chance of getting the laws right, in guessing the laws right. We have a good method in guessing the laws, and this is called the scientific method, and this works particularly well if the system that we look at is very small, because then we have a few laws that are involved in this, like Newton's first and second law, etc. And yeah, so there we had some successes. We are also good in predicting what very large systems will do. So for instance, if the prediction that this water here will boil if I increase the temperature to 100 degrees under standard conditions, this is a prediction that will work very well. Why? Because for systems that are very, very large, and by large I mean here 10 to the 28 components or something like that, statistics saves us, particularly if we have weakly interacting systems. Then we can find some statistics that apply to this. Individual behavior averages out, and we can put this very nicely into laws. Okay, and now how many systems are of this class that we can reduce them to such a small number of components that we can describe every individual law correctly, or that they're really so large that statistics basically tells us we don't need to care about the individual laws. And I would argue that most of our systems are actually of neither type, and this method breaks down there. And most of the systems that we have to deal with in our daily life are complex systems. So what are complex systems? They're something in between. Well, they are too multi-layer, too big in order that we can get all the individual laws right, but they're also too small and interconnected that we can really do statistics with it, because statistics often assumes, as you might have heard, that certain behaviors are independent from each other. And as soon as you have strongly correlated systems, then it's not clear anymore how you can define, for instance, a mean value, a standard deviation for this kind of system. So these things become shaky quite soon. Okay, so what are complex systems? let's make this a little bit more technical. I'm not going to get very technical today. So complex systems consist of a lot of components. These components have certain properties and interact with each other. And the important thing here is the details are matter. So who interacts with whom, under what conditions, this is important. This is what defines the system. And now we come to the point that makes a complex system a complex system. So a complex system is characterized that you have, on the one hand, interactions that change the properties of the system, of the components. As the components change the properties, they change the interactions that can take place. So what you will have are basically feedbacks between this component space and this interaction space. So you have a system composed of many elements. The elements change their states. When they change the states, the type of interactions that you have in your system changes. These interactions, they can change the states. And this goes back and forth and on and on. There is no better example for this than, of course, epidemics. So here is a cartoon for the waves that we've seen so far. So basically, the loop that we are caught right now looks like that. So say we have a social network, and then we introduce some infected traveler. This is here the red node. Then of course you have these infections spreading along the links in the contact network. So say this person here is then recovered and others get infected. And if this outbreak becomes too large, what do? We intervene. We intervene by telling people to reduce their contacts, by ramping up contact tracing in order to isolate and quarantine infected individuals and those that have had contact with them. And so if the state dynamics here becomes too unstable, so we basically change the interactions that we have in the system. That is called social distancing. That's lockdown. That's what we're doing right now, in the hope that people will now faster recover, the new ones become infected. And once this has been achieved and we are satisfied with the numbers being low enough, then of course we allow more and more interactions and the wave starts all over again. So this is one of the archetypical examples of how what can happen if you have these complex feedbacks between the interactions that you have in your system, and how the states of the elements and thereby the state of the entire system depends on these interactions. Okay, the thing is even a bit more subtle. So it's not only that you have these complex feedbacks. As I told you, typically if we look at complex systems, we look at systems that are to be described as networks. And this is not just a mathematical thing that we like to insist on because no one is taking mathematics seriously otherwise. No, this is really something that has substantial consequences on how the system behaves. And again, the prototypical example that demonstrates why the structure of these networks can play a huge role in what the complex system does is the question of herd immunity. So you might have come across this concept in the last 20 months that the epidemics will maybe be over once we approach herd immunity. This herd immunity thing is something that is based on very simple mathematical theories that basically say, so once you have depleted, so if you have an infected individual, and once you have depleted all the susceptible persons that are in contact with an infected person, then a disease can't spread anymore. Okay, so for instance, if you have a vaccine, and if you vaccine and say this person here has a chance interacts with 5 different people, and the chance that you get infected is say 1/10, then you need to vaccinate maybe 4 out of these 5 people in the neighborhood, and then the chance that there will be an infection is smaller and smaller, and on a population level, the disease won't be able to spread anymore. Well, what we learned from network theory is that this simple argument just doesn't hold anymore. And here is a brief explanation of why this is the case. So what you see here are 2 different ways how a social network could look like. So one is shown here. So this is basically a network where each of us has an equal number of contacts. So we all have, say, 2 or 3 people with whom we share contacts. Here is another type of a network these things are called in the literature scale-free networks or fat-tailed, or networks with hubs or fat-tailed degree distributions. But what characterizes them is that you have these hubs here. So these are nodes that have a much higher degree than other nodes in the network. And what you can work out theoretically is that the more likely the network is to have such hubs, the higher is the threshold of people that you need to immunize in order to suppress spread of the disease. Why is this the case? Because if you we now basically have meanwhile a common knowledge word for these hubs here, those are the super spreaders. And if you have a disease dynamics that is driven by super spreaders, then you have always an enormous amount of people in the neighborhood that they can possibly infect. And this basically effectively increases or makes the number of people that have to be immunized higher and higher. Okay, so or different way of seeing that is if you have super spreaders in your network, then the chance that one of them has also contact with someone who is not vaccinated is much higher than if the contacts would be distributed equally in the society. So for this reason, these networks here matter, and not taking this network structure into account leads then to some wrong expectations that just are not true. That, for instance, if 80% in Austria will be recovered or vaccinated, that this pandemic will stop. For more than one reason, this is not true. Okay, so this is as much as I want to tell you about what complex systems are and what modeling, what the principle of modelings are. So what are the principles on which the modeling here is based. Instead, I want to focus the largest part of this talk into making it clear to you what this kind of modeling approaches can do, what they cannot do, and we're going to mostly talking about what they cannot do, but why such modeling approaches can nevertheless be meaningful, and in which way they can be meaningful. So what can this? So I started the talk with telling you that we are only good in predicting certain types of systems, and this class of systems that we can reliably predict, this is very small. Here's a plot that shows you that pandemics is something that we cannot predict very well. So since the beginning of the pandemics, there has been initiatives like this European COVID forecast hub, and there's actually also a US counterpart to that. And what this basically is it's a platform where different teams can upload predictions from the model upfront. So this is also something that many people who evaluate COVID models forget. You make a prediction typically if you try to predict case numbers before they are observed, and not then afterwards you tell, aha, I have known that this will going to happen, but predictions you typically make about the future. And so these are different universities and groups of people that try to do this in Europe. And so what you see here, this is for September, the forecasts that were in this database for Austria. Okay, so here in September, that was around the 16th of December. And then these were, I think, 4 weeks forecasts that have been made there. And each line here is a different model. I'm not going into the detail how these models work. They are completely different approaches. But basically, you see that, yes, so a couple of weeks later, anything would have been possible here. So these models typically agree with each other. So if you increase the time horizon over which you want to produce such forecasts, they become more and more unreliable, and the models, and small changes in the specifications of this model then amplify over time and lead to completely different behaviors, as you observe here. And this, by the way, this of course is not because these are all poor models. These are amongst those are really people who have are on the top of this game, so to say, and have done nothing for the largest parts of the life. But this is simply because, yes, for reasons that I will touch upon later. You might wonder how the current forecasts look like now as we enter the lockdown. So this picture, so this is a screenshot I've just made before the talk started. on how the forecasts for Austria look like right now. And again, so in about 1 month, the forecasts span an order of magnitude. It appears some models have actually managed to implement the lockdowns to different degrees. Some even have neglected that there is a lockdown, or they say that this won't be enough in order to suppress the case number growth that we have. And even for those that model the lockdown, you see that I mean, the scale hides here something. I mean, this is 1 million active cases over 1 week. But you see also here, for those that anticipate that the case numbers now as a result of this lockdown will increase, it's not really clear whether the increase will happen already this week, if it will happen next week, and if it is decrease to a couple of thousand or to 1,000, 5,000 or 10,000 cases in a couple of weeks. So keeping this in mind, so here, of course, we have to ask the question, so why are these forecasts so poor? Or let's not say poor, but so different. And there are two factors that combine why making forecasts is not trivial when you have to deal with infectious diseases. And I quickly want to shed a light on both of them. One I already have mentioned briefly, that's the sensitivity of the models. This is a technical aspect that I will not touch upon too much, but one that is, I think, much more important, and it has led to tons and tons and tons of confusion, is structural uncertainty. And that is an uncertainty that we do not face very often, and that some might even be aware of that this exists. And so I want to talk more about structural uncertainty and less about model sensitivity. So what is structural uncertainty? This means we do not know the correct model. I'm briefly talk about two works from an epidemiologist called Npis, who has also done some works on quantifying the effects of non-pharmaceutical interventions. And I want to show you the, in my humble personal opinion, best and worst paper from him. So this is, I think, the most informative paper where he's a co-author on the effects of non-pharmaceutical interventions. And there they basically showed, studied 3 different models and showed that these 3 different models arrived at completely different conclusions concerning how effective certain interventions are. Why? For the reason that we don't know what the correct model is. So this has to do with, so if now this, we have now this lockdown coming into place today. So which kind of contacts will people reduce? How do this, and all these behavioral parameters, there is no theory from which you can predict this. You can just make any assumptions, and a different way of assuming that this contact reduction will occur across different settings. Okay, so first thing that we take note of is we have to deal here with structural uncertainty. That means typically we have to evaluate something across multiple models. We published a study on the effectiveness of Npis for the first wave, where we also recognized this problem. Our approach was that we use 4 different models. Okay, so here are the main results from our study. And you see here 4 different columns. So these were 4 different models that we used. This was basically a case control design. This was a Lasso regression. That was a random forest classifier. And this was a transformer neural network. And the idea that we had is, so we basically built a database that contained in the end about 80 different countries. And we started here this 36 different interventions, non-pharmaceutical interventions that were implemented in the first wave. And the idea was to use 4 different models and measure whether they find across the different countries that these interventions here had an effect in curbing the pandemics. And by curbing the pandemics, I mean that they have reduced the effective reproduction number. So for those of you who don't know what the effective reproduction number is, so this is this R, or R effective, and it basically tells you how many people on average are infected by one person who is already infected. If this number is above or below 1, this means that the pandemic is accelerating or is decelerating. Okay, so, and our approach here was, okay, use the, and actually we used then more than one data set, but 3 different data sets, 4 different methods, and try to form a consensus across different models. And the result was that, yes, we find some measures that were effectively reducing or curbing the pandemics in all models that we considered. And actually the top, so the most effective measure was small gathering cancellation. So this means that it basically impose restrictions for all places where groups of people gather over longer periods of time. So small gathering cancellations, they concern, for instance, home office, closure of businesses, etc. The second most effective measure, and I will come to this a bit more during the talk, was closure of educational institutions. Okay, so this these two had, you see the ranges of reductions in are effective here, but basically they reduced the infection spread in something between 20 and 40%. However, you also find that there are non-social distancing methods that work quite effectively. So particularly in the early phases of the pandemics, border restrictions, increasing the capacity of the healthcare system by PPE, also personal protective equipment, individual movement restrictions, and then mass gathering cancellations also played a role. And then behind these measures here, the other measures where we find that they, at least in 3 out of the 4 models that we considered had a significant effect on reducing the virus spread. Those were risk communication methods. So these you basically find here. So this means that we consider the different types of communication measures, one that targets specific subgroups of the population, and one that targets the general, and one specific stakeholder groups. And for both of them, you also find an effect. Okay, so you can do something like this ranking of how impactful are certain NPIs were. And keep in mind that these results that I've shown here and discussed here, they refer to wave number 1. Okay, so this was the early phase of the pandemics, when basically everyone was exponentially scared of what's going to happen now. And I will also show you some results how this has then evolved from wave to wave. But for now, I want to briefly discuss, I'll show you in a little bit more detail what the structural uncertainty boils now down to. So these are our results for small gathering cancellations. And this here means has no effect, and we find our values distributed over this area here. Okay, this is the change in the effective reproduction number. Now, for writing a paper, this looks fine, because if I have a highly significant effect, and yes, you can publish this then, well, if you're one of the first ones to measure this effect. But let me translate you into epidemic curves, what this confidence interval actually means. So this means, let's assume, and this is not so far from the situation that we've had in the last couple of weeks, you grow with the effective reproduction number of 1.25. And then you impose a measure like this here, small gathering cancellation. And then it's equally probable that the true effect or the observed effectiveness of this measure will lie here or there. And if you translate this into these curves, the difference is whether you take this curve or that curve. So whether you still stay in a growth phase, but just the steepness of the curve has decreased, or if you can really decrease the number of cases. And depending on in which scenario you go there, you might be tempted to say, okay, so either this measure doesn't work at all, or is overly excessive and is not needed. And this is structural uncertainty that you have here. Okay, we know these things are effective. We know they have a certain bandwidth, a certain confidence in how effective they are. But this bandwidth, this confidence intervals that we have here, they contain completely different scenarios from a policy perspective, because now we are interested in bringing the numbers down. And yes, so this is the impact of structural uncertainty. What you see here, this is still here basically a reference to a preprint, but this has also been recently published now in Nature Communications. This is how the effectiveness of measures was observed in the second wave in Europe. And here, so again, it's measured in reductions in the effective reproduction now, in reduction in the effective reproduction number R. And there you observe now that there are some changes to wave number 1. And the most notable change concerns educational institutions. So for the other ones, we still have highly effective closing, for instance, businesses and gatherings of people. They have also evaluated here mask wearing policies. Those were reduced this by say 10 to 15%, as did nighttime curfews. However, for educational institutions, we've had here around maybe 7%, and just show the result that we previously had. And here this was around 20%. And let me also say that this I show you this now with the example of these 2 specific studies. But the fact that the closure of educational studies, the closure of educational institutions was one of the most effective measures in the first wave. This holds. There are also now systematic reviews out there where this has been confirmed. So this is already quite robust observation. But what is then maybe a bit more surprising is that in the second wave the contribution was much less. And how to understand this, I will also show you in the final part of this talk. But for now, let's just observe this, that also for the same measure, it can have completely different impacts depending on the phase in the pandemics in which you evaluate that. And one of the reasons that contributes to this, by the way, was also that in the first wave, the closure of educational institutions was typically one of the first stronger social distancing measure that was applied. So certain measures also have a signaling effect, and if you close the schools, you basically show, hey, now really something extreme is going to happen, and this is what to some extent contributed to wave 1 next to other factors, and which wasn't so much the case in wave 2. But for now, I want to focus on a different aspect here, and this is what happens if you combine measures. Okay, so for instance, this here tells you, okay, if you close the nightclubs, then you would have to expect a reduction in the effective reproduction number of say around 10 to 15%, and the same for nighttime curfew. Now it goes without saying, if you close the nightclubs and make a nighttime curfew, then you can't expect a reduction in 30%, but just adding this, because of course these interventions will eat itself up. So what we observe in measures are that they are sub-additive, meaning that you can measure the effectiveness of a single intervention or of 2 single interventions, but the combined intervention typically has a smaller effect than you would assign to the 2 individual interventions. And you also observe this if you try to add up these contributions here and see that you won't arrive there. And the reason why I'm stressing this is because now I'm coming to the I showed you one paper of Ioannidis, and this is the ones that this is another one, which is used in a lot of discussions about that lockdowns don't work, and that Ioannidis has shown, and there is the Stanford study that has shown that these measures don't have any effects. And now here I want to use this opportunity to show you the methodological error that there is in this study. So what happened in this study was that they also tried to quantify the effects of non-pharmaceutical interventions, of NPIs. And what they did is they introduced 2 different types of NPIs. Those are the more restrictive NPIs and the less restrictive NPIs. So more restrictive NPIs you can see as a proxy for lockdowns, and with less restrictive, you mean something like ramping up contact tracing, etc. So, and this is how they evaluated the effectiveness of individual interventions. So they assumed that the effects of more restrictive NPIs are computed as follows. you compute the effect of all NPIs, and then you subtract the effects of these less restrictive NPIs. And then, with little surprise, the result was that more restrictive NPIs don't have much effect, which shouldn't really come now as a big surprise at all, because we've just discussed here that if you combine measures, they are sub-additive. And here is another visualization or result analysis that shows you this. So this here the authors reported a combined effect of all NPIs. So if all NPIs that we have ever observed, if you combine them at once, then you achieve a reduction in the reproduction number of around 75%. The remaining 25% are, by the way, household contacts, and we usually don't isolate everyone in the household alone. And again, if you combine now this, if you sum up now this individual measures, then you typically get less than, typically get more than the combined effect of all NPIs. However, if you were to now evaluate the effectiveness of, say, cancellation of gathering by subtracting from that value the sum of all those, then you're obviously doing something wrong. And yeah, this is why this Ioannidis paper about lockdowns has to be really read with a large grain of salt. Another thing that to note here, and this is something that particularly for communication of how the pandemics unfold is quite an issue, is what you see here. So this was one of the first measurements that we've had for the seasonality component of how the virus spreads. And this shows you how the effective reproduction number is modulated over the year in different weather conditions. And yes, so you see basically that between the summer and winter, you have an increase here of up to more than 40% in how much the virus transmission accelerates as you go into winter. And this is something, of course, that also contributes to the situation that we're currently in. However, and this is the message that this plot shows, this is not something to which you can do nothing about. So that the situation is that, yes, seasonality is a strong contributor, and each individual intervention that we know of has less contributions than seasonality. However, the combination of individual NPIs can more than counter seasonality. And I think this is the important message here, which tells you that you really need something like a multi-layered approach, because with one intervention alone, these effectivenesses that you observe are just not large enough that you can really counter the seasonal impact. Okay, so this is what I wanted to tell you about structural uncertainty and how it impacts our ability to make statements about how the pandemics will unfold. And now I just briefly want to share with you a result concerning model sensitivity. And I think this plot here tells the story. So I've said that structural uncertainty means that you do not know the correct model. Now you can do the following: you take a computer model for a pandemics and make a synthetic epidemic wave, and then you try to forecast this synthetic wave based on incomplete observations. So, for instance, you know the computer model, and this generates you this circles here, and then you take the model and then you try to predict without running the model. Okay, how will this epidemic unfold, given that you make certain interventions? And the clue of this is that this takes out structural uncertainty, because this is a computer-generated pandemic. So you know the laws, the natural laws that govern this pandemic. And every error that you can then make is just how well you managed in order to fit the parameters that govern this model. Okay, so like the effective reproduction number, like the transmission rate, etc. And what you see here is how good this works. So if you are given some observations from the computer-generated pandemic, if you know the real model, and then you try to fit this model, how well does predictions work? And here, again, the active cases, and here you see this is a logarithmic scale, okay? So you have here 1 cases, 10 cases, 100 cases, 1,000 cases, 10,000 cases, etc. And if you put this on a linear scale, then this plot shows like that. This is not so different from the forecasts that I've shown you in the beginning from the forecast hub, where we've also observed that after a couple of weeks, you have confidence intervals that span various orders of magnitude. And here they show basically the same principle now for a real pandemic, which then, of course, the confidence intervals are even larger than if you try to predict one where you know what the correct model is. Okay, so this makes forecasting how a pandemic unfolds such hard business, because you have these two types of uncertainties that both have an enormous impact on your ability to make any statements about how this will play out on the longer term. So at this point, you could just throw your hands in the air and say, okay, if these models are not meaningful and don't work, and if all the confidence intervals are so large, we should, why bother? Why do it at all? And the answer is very simple. The answer is a decision has to be made. We have to make decisions about which settings to close right now, what is the appropriate level of Npis. These are decisions that have to be made if we don't want to inflict extreme casualties on population health. So despite all these differences, at least those things where we can make valid statements, we really need to make an effort in order to bring this evidence to bear. So decision has to be made, but how does this work? How can we now? So what I've shown you so far are mostly academic works. So how can we now condense this into something that may or may not be useful for policymakers, for decision makers? I don't claim that I can answer this question. I just want to tell you that how we basically have approached this. So I think you have to distinguish between 3 different disciplines in what you can do with this kind of forecast models. And the one is the short-term forecasts that we make in the Prognosis Consortium. How they work you see here. So basically, for the reasons that I've already explained, we make a multi-model forecast. So we have 3 different models that make forecasts, and then we harmonize these models. And what you see here are is basically the reporting from today. So this was taken from today, and we made the last forecast we made last week. And we forecast 3 things: the cases, those are shown here, the ICU usage, so how many beds are occupied at the ICU, and how many beds are occupied in the hospital. And here, by the way, is the effective reproduction number. And then you see 2 weeks ago, we had an R of approaching 1.3, and now we are already down to about 1.15. You see here this different. So at this point, we made the predictions, and these are the confidence intervals. So these have been measured based from how well our past predictions work. And what you see here are these dots here. Those are added day per day, and we put them in different colors. And green means, okay, the epidemic is playing out as we have expected a week before. And then we put it yellow or red if we severely over or underestimate what has really happened, and this for any of these 3 signals. And basically here you see how well this has worked in the past. So this is so for the past 3 waves. So this here is the ridiculous wave number 1, wave number 2, wave number 3, and here you see the effective reproduction number. What you see here is a time series of how well the predictions did work, so the relative differences from the real case numbers. And here there is one thing that I want to emphasize here. So these are the 3 different models, these 3 lines here. Okay, so one is the model from our institute, one is the model from the TU Vienna, from Niki Popper's group, and the other one is a model that the Austrian National Public Health Institute has developed. And what you see here is it's very rarely the case that that there is a clear best model here. What typically happens is that the dynamics of the pandemic changes via a short period of time. You see this here in these fluctuations of the effective reproduction number, and that none of the models anticipates that, and the models together over or underestimate what happens. And I would argue that this is the value of this forecast system that we've built up here. We basically signal, okay, the epidemics has progressed as we would have expected, or hey, now something has happened. We have to put their red dots and tell them, look, the ICUs are growing faster or slower than expected. Something, and this is now out of the confidence interval, so something has to have changed here. Let's take a closer look at what's going on here. And these are typically the signals that we extract from that. So this is one added value, and the other added value, of course, is that for ICUs you can make some longer predictions, simply because the dynamics is derived from the case numbers that we've had over the last couple of weeks. So this is the first discipline for the first lecture. So you can make something like short-term prognosis, but short-term here means a couple of days. And the signal that you're then after is whether you are still on track for this forecast, or whether you observe it at change points in the dynamics. The second discipline are scenario simulations. And this one that we did here at the end of August was was referenced in the media once or twice in the last couple of weeks. And there we tried to formulate different scenarios of how we thought in the summer that the winter might play out. And so basically we made, and this is what is different between a forecast and a scenario modeling. For the forecast, okay, we provide one line. So this is how we see the future. This is as far as we dare to go. Here we said, there are certain factors that strongly affect how the pandemics will unfold, and we don't know how these factors look like. And here in particularly, will we still make any progress with vaccinations? Will we remain at 62% of the population being vaccinated once we enter winter? Or will we, for instance, manage in some way or another to progress to 70% of the total population being vaccinated? And if then everything stays the same, this was the basis scenario, and we don't make more vaccinations, then this is what we would have expected to occur. So again, you see, for reasons already discussed, large confidence intervals, but basically the most likely evolution was something where between October and November, we would approach close to 10,000 cases per day, and the confidence interval going up still also includes 20,000 or 25,000 cases per day. And basically the red area here means if you enter these areas, then your ICUs are working at or beyond the capacity. And yes, so this is the second thing that we try to do here. You all, I guess, followed in the news whether this worked or not, but so the point why I want to reference this is because here I also show how we tried to inform the decision makers back in August then what's going to happen, what might be needed, because we've then run scenarios and said, okay, so if, for instance, we manage over the time span, even if we don't make any progress in vaccination, but we reduce the effective reproduction number by any means by 20%, then the chances that we will get into trouble here are substantially lower than it's here. And then this is basically what we described here. And then based on the results that I've shown you before, we can also say, okay, what does it mean if we have to reduce R effective from minus 20%? And this you can look up in studies like this. If we want to reduce it by 20%, basically we need to impose, for instance, a nighttime curfew. So mask wearing policy we've already included there, but you basically need a nighttime curfew and you need restrictions of larger events, something of that order of magnitude. And this was something that we tried to flag back then in August and in internal discussions since then. And and you know what happened. So this is how we try to deal with all these uncertainties. So we have the uncertainties that come in trying to estimate, okay, will this be 5,000 or 10,000 or 20,000 that we have to deal with at the peak? Or and what are the appropriate response measures? So if we go for 20%, then yes, there is still some. This still means, okay, we might have. It might suffice to just make a nighttime curfew and cancel public events, but we might also have to additionally send people into home office. This is not really cannot really be anticipated more clearly. Okay, and the last thing, the third discipline that I want to show you that is different from the first two is that we try to make models for specific settings. So here we basically talked about interventions that you need to put in place for population-wide. Now we've also talked in the beginning a bit about schools, and now I want to make this more a bit in depth and tell you about some work that we did and how this impacted policy or not impacted policy when it comes to protecting schools. So as you know, this is a quite emotional issue, and we really had wanted to assess what kind of evidence is there and what can you say about what is this feasible at all to try to keep the schools open as you have a pandemic that is going on. And when you have sustained community spread under such conditions, can you have the schools open or not during such a simulation? And what we did here is that we developed an agent-based epidemiological model that was calibrated to Austrian contact tracing data. And we looked at different non-pharmaceutical interventions, so like ventilation, the wearing of masks, student cohorting, and back then when we did this, we also looked at antigen screening and not yet PCR screenings. Since then, we've also incorporated characteristics of the Delta variant and of that now, of course, some of the levels we can vaccinate. And so let me just briefly show you some data to which we calibrated the model. So this was in a collaboration with AGES and the Institute for Epidemiology of Infectious Diseases. And the data set that we used were 616 infection clusters with transmission in schools. This was autumn of last year. And these 616 infection clusters contained 9,200 cases, of which 2,800 were students and 670 teachers. So in order to understand this data, you need to understand what is meant if we talk about an infection cluster. Basically, a cluster is everything where you have one index case where you don't know where this case comes from. And then for all other cases where you can find some connection with the index case, this you put into a cluster. And there we looked at all clusters where there was at least one transmission that was taking place in the school. And then you can look at what are the distributions of these cluster sizes, of these clusters across different school types, whether they were symptomatic or asymptomatic, etc. And yeah, here maybe an interesting finding from this. So this is, I've said at the beginning that in complex systems, it is often the case that you have to deal with systems where something like mean values, average values lose their meaning. And I think this example shows it very nicely. So 40% of the school clusters that we have, they consist of two cases, meaning that you have maybe one index case in school and then there is one infection and then the cluster stops. So almost half of the clusters that we observed during that time in schools consisted of two cases. However, 3% of clusters contained more than 20 cases. And these are very typical distributions that you observe here. And this, of course, then goes back with super spreading events, etc. And this basically means that if you compute the mean value, the average cluster size here, then this would lie somewhere around 5. However, this mean value, one infection cluster contains 5 cases. This doesn't really tell you anything what's going up because you have a very skewed distribution. Half of the clusters contain one index and one follow-up cases. And then you have a small percentage of clusters that contain an enormous amount of cases. And yeah, nevertheless, you somehow need to communicate this in simple numbers, and this is often a challenge because we like to think in typical sizes and averages, but they just don't apply here. And I think the school example shows this very nicely, because I think we've all heard reports of classes of examples when whole class was infected. And, yes, this occurs, but it occurs in a small percentage of the total clusters that are observed. And what is much more typical is that these clusters are small. And yeah, but of course, then you have also the other side. So people say, yeah, we've already had so and so many cases in school, but there was never anything happening, and we don't think that the virus is spreading at all in schools. Yes, most of the clusters are small, but with some chance you have very large clusters. And I think this shows you very much about how the simple fact that you have here a statistics where the mean value, the average, doesn't have any meaning, how this complicates how it complicates this to assess the risk that comes from such settings. Okay, and notice not only that this risk is very hard to express, it's also that we now need to quantify the effects of interventions and how they change this distribution. And before I show you some of the results, this is what has to be stressed here. There will be no perfect intervention that can rule out that something like this here happens. But what should be the aim of any meaningful mitigation measures is that you have more and more smaller clusters and less larger clusters. But there is hardly any way in which you can rule out that you will still have at least some of these larger clusters. Okay, so just very briefly, what did we do here? Then based on this cluster tracing data, we basically developed an agent-based simulation model where we not only measured how people become infected and recover, but also how their virus load develops in the host in order to meaningfully model the test strategies. So at which point can an infection be detected? When do you become infectious yourself, etc. And since we are now having the discussion about so how age plays a role here in the infection dynamics, I just want to show you one simple fact that is, in my personal view, not really appreciated in the way it should be. What is so different if we compare primary schools and secondary schools? And this has not to do with the virological characteristics, if the virus load in children is as high as in adults or not. But what you see here is the typical social contact network of an Austrian primary school. So these are the classes and the pupils, so the students, they are red. The students live in households. These are these gray areas, these gray nodes. Occasionally, you have it that one household has children that are in two different classes. So this you will also observe. And these are the teachers. And in a primary school, you have typically one teacher that spends most of his or her time in one class. So, and this is how this looks like in primary schools. And on average, an Austrian primary school has this number of classes, etc. So this is how the typical Austrian secondary school looks like. And now, without going into the virological characteristics, it should be immediately clear that the virus spread in such a network will be completely different from the network that we've looked at before. And one of the big differences are, of course, teachers that go from class to class in each different hour. And this is something that structurally makes the virus spread in older students completely different than in younger students. Okay, so here are the results. I'm not going into too much detail here, but basically you see different school types here. You see here the distribution of cases that you observe. And blue and red means whether your index case has been a teacher or a student. And what we show then here is how this distribution of outbreak sizes decreases if you stack different intervention measures on top of each other. And bottom line is also for schools, we need to think of layered approaches, and you need to stack these implementation measures on top of each other. So we won't be able to get rid of this by testing alone. But if you combine testing with ventilation, with wearing masks, maybe with student cohorting, and now we also have vaccinations, then you have a chance. And then you manage to bring down to at least achieve it, that is the likelihood of observing large clusters becomes smaller and smaller. So why I'm sharing this? Because today our Minister of Education, Mr. Fassmann, was basically citing some of the numbers from this study as an argument for why it is reasonable to keep schools open, even under sustained community spread. And you might have seen this debate. So the discussion that we currently have. And one thing that slide that I have now forgot to put in there is basically that we also show how these distributions change when you do not perfectly implement the measure. And then we basically can show if you fail, for instance, if your testing doesn't work properly, if the masks are not worn properly, if the ventilation doesn't work, then of course you can stack as many measures on top of each other as you want, but you won't be able to suppress the spread, particularly with this virus, with this Delta variant. And this is now something, so I would say based on our paper, you can argue for both. If you just take our paper at face value, you could argue, yes, schools should remain open because by layering enough protection measures on top of each other, even under sustained community spread, you can at least reduce the chance of observing large outbreaks in schools, which then could drive again the spread on a population level. However, if you have reason to believe that these measures cannot be properly implemented, then this tells you that the situation could get quickly out of hands if you're too sloppy in implementing these measures. And again, this you could use for, I would say you could use for arguing either position, but that's just as far as we can go there. Okay, so I'm wrapping up. Here's a summary of the kind of statements that you can or should make with modeling works that you should not make. And these are the green here, these are the kind of statements that I truly believe that we can make. Okay, so we can say with a chance of that percent, we believe that the daily new cases will be in a range between say 5,000 and 10,000 in 2 weeks. We can make statements like the impact of a certain measure, let's say a lockdown for not vaccinated, this cannot be distinguished from noise in a statistically significant way. You can also make very firm statements like that in this specific area, in this specific range of time, you expect a seasonal wave that will for instance, amplify virus transmission in a range of this and that many percentage. However, because of all these limitations that I've shown you, these are the kind of statements that no one who seriously performs pandemic modeling will make, and this is, you expect 100,000 dead people. The pandemics will be over at the time so and so. This is not something that you can do with models. The height of the next wave or the peak of the next wave will be, say, 20,000 new infections. No way of telling that. That's where the models are poorest. We can say, okay, it's likely that you will reach a peak within the next 1 or 2 weeks. So in the current situation, I would say we will either peak this week or next week. But if we see a 20,000 or if we've already seen the highest values, I wouldn't dare to say. Of course, also this very simple exponential models, this is also something which we should be well past this point. And one thing that I want to, one anecdote that I want to give for this comment here, because this is something that in some of the deliberations, in some of the discussions with policymakers, they come to you and ask you, so how large do you think the peak will be? And there are 2 answers that you can give to that. The first answer that you can give is, well, I don't know how large this peak will be, but the chance that it will be 10 times as high as we expect now is so large that you should be really concerned about this. This is because this highly skewed distributions that we have to deal with. But in reality, and particularly if one of the policymakers from the higher echelons asks you this question, the answer should be, well, how high the next wave will be depends on what you decide now. Because despite all these limitations that we have seen, the pandemic is something that you can control if you act consequently, if you act fast enough, and if you really see your decisions be put through. So it's not, and if I maybe a bit polemic at this point, it's not that the policymakers should ask us as modelers now how high will the next wave or the next peak will be. It's their policies to determine how high this will be. Okay, and with this, I'm at the end of my talk. Here are some ceterum censeo that you might want to look up into. Yeah, that we not only lead a layered approach in schools, not only in Austria, but also on a European level. And with this, thank you for your attention, and I'm looking forward to any questions that you might have.